Hello everyone. In this video, we are going to look at the diffraction of waves and then interference of waves of a double slit and multiple slits and the interference of white light through a multiple slit. So let's look at diffraction first. So whenever waves pass through an obstruction or through a gap, straight waves will bend a little bit, and this bending is called diffraction. So if we compare these two diagrams, wavelength of incident wave is same, size of the gap is smaller for this one and larger for this one. So as we can see that waves diffract more if the size of the gap is smaller. So that's one thing. And second factor is if we compare the size of this gap and that gap, size of the gap is same, but here diffraction is more because the wavelength is longer. So in summary, what we can say is that diffraction depends on the wavelength, and it also depends on the size of the gap. What it means is, and diffraction happens in all different types of waves, whether they're mechanical waves, water waves, or they're electromagnetic waves, light waves, or radio waves, and all that. So in terms of, if you look at compare the light waves, blue light has got shorter wavelength and red light has got longer wavelength. So red light will diffract more as compared to blue light. Now let's look at what is constructive and destructive interference. When waves from two sources, they are in phase, that means crest lies on a crest. Resultant wave will have bigger amplitude, or we say when they are in phase, a constructive interference will be happening. If they have opposite waves, the waves from two sources, then they will annul each other, and resultant wave will have a zero amplitude, and that's the destructive interference. Now, let's look at the 2-point source interference pattern. S1 and S2 are two sources of waves. So they're producing circular waves, and then they interfere with one another. Now, this is the crest of a wave, that's the trough, and that's the next crest of wavelength is this much. So if we look at all the points in the middle, the waves arriving from two sources will travel equal distances. So path difference will be zero, and constructive interference will happen here. So N or M is zero. And over here, wave traveling from S1 is traveling longer distance as compared to S2, but phase difference is one wavelength, or N is equal to 1. So there will be constructive interference happen. So these are called antinodal lines where constructive interference happens. N equals 0, N equals 1, N equals 2, and similar on the other side. The blue lines are the points where destructive interference is happening. And because of the annulment, so there will be minimum amplitude, or path difference is 0.5, 1.5, and 2.5. Now, this is true for all different types of waves. So for example, if these were water waves in a big pond or something, and you travel from here to there, so what you will have is over here, it will be choppy water because of the constructive interference, calm water, choppy water, calm water, and so on. If these were to sound speakers producing sound, then here you will hear the louder sound, quieter sound, louder sound, and so on. And if these were the light waves, then there will be bright light here, dark light here, and bright light over here. And that's what we look at the next one. So if we have red light shining from two sources, so light will diffract, and then they will interfere. So right in the middle over here, there will be a bright spot on the screen. If it was a red color light, monochromatic light, because the path difference is 0. Over here, path difference is 1. path difference is 2. So these are the bright lights where constructive interference is happening. And these are the values of the path differences. In between over here, there will be destructive interference happening. So path difference for this one will be 0.5, 1.5, and so on. And same on the other side. Now, it's a similar diagram done by hand. So distance between two slits is D. L is the distance from the slit, double slit, to the screen. And that distance is measured, or it is called X. So if we are measuring from here to there, that will be only, N will be 1 for that. However, if we measure from here up to there, so N used will be 2. But if we measure from here, say for example, from here up to there, then N will be 5 because, N will be 4 if we measure up to here. So from 2 over here to 2 over there, if that's the total X, then N will be 4. Or what's the formula? Formula is path difference is XD over L. X is the distance that I mentioned. D is the distance between the two slits, and L is the distance from the screen. So N is 1, 0, 1, 2, 3 for constructive interference, and 0.5, 1.5, and so on for destructive interference. Now, in a monochromatic light, if there is red light, and then we, instead of red light, we shine green light. Green light has got shorter wavelength, so it will diffract less, so pattern will be closer as shown over here. For multiple slit interference, so this is what we call as a diffraction grating. It has got many, many gaps, which are, and in between there will be glass opaque areas. So that's called diffraction grating. So light passes through all of these gaps, then it diffracts, becomes circular, then they interfere and make an interference pattern. What will be seen on the screen will be a bright spot in the middle, and the second bright spot, it will be further away as compared to the previous pattern, and so on. So N is equal to 0 for this one, N is equal to 1, 2. And because there is a quite lot of distance between these one, so instead of measuring distance in terms using XDLL, we measure the angle. So that's the central point. It's called the central maxima, first order maxima, second order maxima, third order maxima. So if we measure this angle from here to there, then N will be 1, and that will be the angle. If we measure angle from here up to the second order maxima, then N will be 2, and for N used will be 2, and that will be the angle. Now, if the number of slits per meter is N, then the distance between the slits will be 1 over N. And path difference is equal to D sine theta, or N lambda is equal to D sine theta. So N is used from this diagram. So depending on what angle you're measuring, you will have to use the appropriate value of N. Now, if we want to find out using the same thing, so how many, this is a central maxima, that's the third order maxima, how many bright spots will be seen on the screen? So if light was going straight, that's the straight path. So maximum angle of diffraction is 90 degrees. So if the question is asked that how many dots or spots will be seen, or how many maximas will be seen, then we use sine theta will be sine of 90 degrees. And if we make this one as sine of 90 will be 1. And then N will be D over lambda. So that's how we can calculate how many d over lambda, how many spectrum can be seen. So n will give you the number of spectra. One more thing, that this gap over d has to be close to the wavelength. If it is gap is larger, if this one d is larger than the wavelength, then that means sign of this one will be greater than 1, so nothing will be observed, and reason for that one will be that maximum angle diffraction is more than 1, which is not possible. So what you will see over here is that on the screen there will be just a bright patch of red light instead of individual dots. Now, what's the difference between this pattern, which is a multiple slit interference pattern, as compared to double slit, as shown down here? Okay, so red light has longer wavelength as compared to blue light, so red diffracts more, or blue dots will be closer and red will be further apart, green somewhere in the middle. Now, with the double slit pattern, these dots are very close to one another. Okay, so that's why we use the formula n lambda is xd over L, and for this one, n lambda is equal to d sine theta. Another thing that you can notice is that these dots will be brighter as compared to these one, and they're further apart as compared to the double slit pattern. Now, instead of using a diffraction grating, instead of using one color light, if white light is shown on a diffraction grating, what is seen is white light in the middle and then spectrum on either side. So blue is seen towards the center and red is towards the outside. So this is called the central bright band. First order spectrum, second order spectrum, and same on that side. Why red is outside? Because red light diffracts more than the blue light because it has got longer wavelength. Okay, similar pattern. So diffraction grating, center bright band. So n is equal to 1 for the first order spectrum, n is equal to 2 for the second order spectrum. So if you have to find the angle, at what angle will the red band be formed, then we measure this angle from here to there. If you're asked to find at what angle will the bright blue band formed, then you will measure this angle from there to there, but n will be 1. So the formula is same as we used previously, and lambda is equal to d sine theta, but lambda will be if it is red light or blue light. Now, why is a white band formed in the middle is that if there was a single color light, for example, red light, you will see a red spot in the middle. If you were using a green light, you will see a green spot here, and the other orders bright spots. If you were using blue, it will be blue light here. So in white light is made up of all 7 colors. All 7 colors are being constructively interfering here, so making it a white band. Where over here, there's destructive interference happening here, and here only the blue light is constructively interfering. Here only the green light, or here only the red light is constructively interfering. So that's the pattern with the white light. And again, if we have to find the number of how many spectrums can be seen, maximum angle of diffraction is 90 degrees. So you make this one sine theta is sine of 90, that's 1, and calculate the value of n from there. Okay. This one is just showing the same pattern on the sideways, so white band in the middle and the spectrum on either side. If it was a single color light, green will have the same position as the green in the white light. So this is with the monochromatic light, this is with the white light. So this is all for this video. Thank you for watching it.